Okay, next on our agenda we have James Lewis from Red Semiconductor, who's going to be talking about bio-inspired codecs using stenography. Right.
No.
I don't think it was. I read that and I thought, that's not right.
I do not even know what those words mean.
This is someone else who is not you.
It is.
You're going to be talking about, I know what we're going to be talking about, VISC, right? So,
yeah, exactly. I'm going to talk about how you make simple processes like RISC-V.
Let's find out what it
do
says.
clever things and go faster and solve some AI problems. But yeah, read out the book. They have ways.
Can you find it?
While you're doing that,
yes,
absolutely love the reference to ancient manuscript stuff because it reminded me my daughter studied all sorts of languages at university, one of which was Finnish, and back 1,000 years ago, when nobody could write stuff down, they had a set of rules that defined how the traveling news tellers went from village and town to village and town, and they had to follow a code which was number of syllables in a line, rhyming, articulation, and alliteration, and all sorts of things. A set of rules, set of code, so that if the newsreader thought, oh, I didn't like the fact that Harry beat George in the battle of such and such, I'll go to some village and tell them it's the other way around. They'd work out that because of the meter and the syllables and stuff, they go, hang on, you're just telling us a
it wasn't right.
And they could actually work out what was correct because they had to fit.
That's what you mean.
These days we call it forward error correction. We use it everywhere. So yeah, amazing.
Interesting story. I'll tell David that. Right. So James Lewis from Red Semiconductor. So you're, I think, going to talk about a semiconductor core IP called VISC, which is created within the requirements both to be compatible with standard RISC-V architecture and to innovate for differentiation.
Sort of, yeah. I think all that's in there somewhere. Can I have the?
Off you go.
I realised I put in 2 first slides, so I mean, move to my. No, I'm going to talk about. So RISC-V is an architecture that's been around for a long time and is well used, well understood. Is there room for innovation within that architecture? It's all written down in a book, and lots of people have designed it by the book. There are various threads of innovation. There's innovation of how many of them you use and what you do with them, and how big and how small, and innovation in how you improve the performance of RISC-V. And we're associating it with the issues of bringing AI to the edge and how we apply that innovation to achieve that. So we've created something that we call VISC, Versatile Intrinsic Structured Computing. More anon. But the driving forces are obvious. Oh, this is not going to be a how to do it lesson for everybody. It's a sort of it's a story of how we thought up an idea and put it into a company, and a little bit of my own background and lessons I've learned along the way that I've been inspired by, and maybe there's a bit of inspiration for those of you a bit younger than me and starting up things at the moment. So right now in Red Semiconductor, we are trying to do the following. We're trying to create an accelerated technology that effectively is pre-pipeline. It goes in front of a standard processor architecture, RISC-V for now, but others to follow. And it's also all about efficiency, getting the maximum efficiency out of the processing core, and using a bunch of techniques to expand and enhance that, all the way up to a better way than just repeating a core, step and repeat. Let's have more cores. No, let's not do that. Let's make let's get the cost and the area down by only parallelizing a small amount of the core. And the objective really is continuous mathematical algorithms that are run in real time. And we filed a patent on it, so I'll talk a bit more about that later. But this is kind of obvious. I've never come across somebody who says, no, I want to process less data slower. It's all going in one direction, but they don't want to pay for it. We're in this funny industry where, you know, imagine we were bakers and people kept coming to us year after year after year and saying, no, a loaf of bread's got to cost half what it cost last year, half. Chips is just this natural thing. Somehow we make them cost less than they ever did before for way more performance, and these trends are carrying on. And up until recently, up until now, we've had a pretty good way of doing that. And it was described by Moore and therefore named after him as Moore's law. Make the thing go clock faster so that you can do more stuff in a second. And how do you do that? Well, you make transistors smaller. So and you're chasing the power consumption associated with clock cycles and power consumption reduction with smaller transistors. But what we do know is that as that progresses, the whole thing gets way more expensive, and to the extent now it's pushing some laws of physics to their extreme. Much debate about that. So, given that there are those limitations in the traditional way of doing this, we've got to go back and have another thing. And the way we've done it is that we've been inspired by some history in computing, some things that have been done for other reasons in the past. Now we've brought them all up to date and we're sticking them into our accelerator technology. So it's a case rather than throwing the same set of things to solve a problem, just come in and think about it differently, come in with a slightly sideways view of it. And they're called accelerators. So accelerators are well, in everything we hear about accelerators in pretty much every design, and in general. And I know I'm sort of dumbing this down a bit for ease, but effectively, an accelerator sits in a process-based system or architecture, and the processor says, "Oh, I've got something here. I've got an accelerator over there. I'll give it to him to do. Right? What have I got? Oh, got something else. I'll give it to this accelerator." So the acceleration depends on the processor's involvement, which burdens the processor, slows everything down. And those accelerators that we see today are quite specific to functionality. There's a DSP accelerator here, a matrix multiply accelerator there, such and such accelerator here, and you're not using them all at the same time. So basically, you've got quite a lot of silicon sitting idle, doing nothing, costing you money. So our approach is what we call inline acceleration, VISC inline acceleration. We accelerate pretty much everything. If there's a boring old bit of control code coming through in RISC-V opcode, we just pass it through. But anything that has been written with a view to accelerating repetitive real-time processing, we get in the we get VISC involved in the process and speed it up. So it's an efficiency of the processor. In fact, an engineer who was talking through this with me the other day said he kind of turned it on. You know, it's almost like the processor just accelerates what you're doing at the front. You know, VISC becomes a flow controller, flow of instructions, flow of data, flow of everything, and the CPU core does what it's best at, just chunks data through. But the right data is always in the right place at the right time for the next instruction to be executed. That's where that efficiency comes from. A bit about my background and how kind of lessons learned in the process. A long time ago, as an applications engineer covering National Semiconductor project, who remembers that National Semiconductor actually had a very advanced 32-bit processor called the NS32000. It was a great processor, had some really good, clever features about it, one or two which might have found their way into VISC. But at the time, the market was dominated by incumbents, Intel doing rather well with the x86 architecture, and Motorola with the 68000 that became sort of very embedded and used everywhere. And they basically failed to accomplish what they got a great processor, but failed to accomplish the commercial objectives that they wanted to, and they reversed out of that. That was a bit of a shame. And then my next sort of interaction with interesting processes. So I founded a company called Oxford Semiconductor in 1991 or 92, and then by about 96 we were building quite a complicated chip, and in those days verification of chips was rather different than it is today. There weren't the tools, there weren't the people, weren't the experience. We knew we were going to have some difficulties, some problems in it. So we stuck an ARM core in it. Why did we stick an ARM core in it? Not because we needed programmability, but because we secretly around the back wanted to put right the cock-ups that we would inevitably make in rushing the chip through to production. And rush we did, and it worked. And we sold millions, tens of millions of this series of chips. So this was a great success. And the other good thing, we didn't pay a cent to ARM in license or royalties because Samsung had basically done a deal to enable them to continue being a company. And we got our chips fed by Samsung, and happy days. Anyway, after that, I went and did other things and ran a couple of other companies. Found myself at a slightly different company, trying to solve a complex problem, which was jamming and spoofing of GPS. And the company was founded by a very accomplished antenna engineer who believed that all the woes of GPS could be solved by better antennas. Better antennas definitely help. That's a great thing. But actually, if you talk to the market, it's another good thing. Listen to what potential customers and people in the market say. How are the problems going to be solved? More processing power. So we devised a system where we wanted to parallel process multiple streams of data, do really complex trigonometry, because in an array of antennas which are a few centimeters apart, we wanted to look at phase difference and therefore angle of arrival of signal from the satellite 20,000 kilometers away. So it was all quite difficult and couldn't afford what ARM wanted us to pay for that. So that got me interested in processor cores and took me down the road to what became Red Semiconductor. So pursuit of the RISC-V architecture, the price is right. It's very open, and we can make its performance right. And for us, it's a great sort of innovation opportunity. Let's go and do something. So a little bit about AI and taking AI to the edge. Obviously, generative AI, you've got lots of people typing away, do me a market report on such and such, write my homework in the style of Bertie Wooster, whatever it is, and you've got centralized compute resources, which we read every day about great big sort of data factories with power stations next to them. This is a problem, and it's a problem that is only projected, not me predicting this, it is going to get worse. How do you solve that problem among the various other problems? And why do we want to get AI out to the edge? There are many applications, sort of things covered by the icons there, and there aren't users of this AI. There are beneficiaries of it, but the developers develop the AI systems to work, and billions of people will benefit, but not even know that they're benefiting from it. But on top of that is, how do you get, so as we move from large language models to the LRMs, then how do we get the AI processing away from a data center and into something you can hold? And why do we want it in something you can hold? Yeah, great to be able to do everything we do with ChatGPT at the moment while you're mobile. And I know we can access data centers, but to be able to do it absolutely guaranteed, instantaneously in the palm of your hand is really a goal of this industry. It's a long-term direction of this chip technology, but to start with, typical edge processing demands, many demands where you need decent amount of processing power, you're creating situational awareness. You're looking for anomalies, changes, or whatever in that situation, and then as a result of that change, you're saying, I need to act now. And then you're probably following up with some communication, whether it's a check to other people who need that data, or simply a paper trail so that you can prove why you were right in making that decision in your AI. So yeah, effectively responding to change in situations and doing it immediately. And this really does cut across all market sectors. So anything where there's sort of AI, machine learning, cryptography, any kind of trigonometry or mathematical functionality going on covers so many market sectors. And the requirements, the driving forces are obvious rather than going through them all. Yeah, we instantly know what the use case driving forces are to do this. So a bit about VISC then. So as I've said before, mathematically oriented accelerator, and what we're seeing at the moment, and do the maths how you will, and you can multiply performance benefits with power saving with such and such together. It comes out, big numbers. These are orders of magnitude saving you get. I'll show you a bit more in a minute. And we start off with what we call abstracted instructions. Well, they are abstracted instructions. So an entire function is described in a sort of metadata-rich single instruction, which means that the VISC unit has got the whole context of the algorithm it's trying to do in its memory, and also because it's translating to RISC-V instructions, it knows exactly what the processor resource availability is. So all the time it is matching workload with resources. That's basically how it does it. I've just said that bit. So it's a mixture of instruction and hardware. And in the hardware, it's a set of functions that do things like vectorize, reordering instructions, reordering data fetches, reordering register locations for optimal context. And we've applied for patent, and it's going through without any problems at the moment. So it appears that nobody else has thought of exactly what we thought of up until now. In terms of our process of verifying what we're thinking about, obviously the design process takes concept and figure out what you want to do, define it, and then in our case we've started on the instruction set and the hardware architecture using broadly open source tools. Egosys as a bit back-end tool, but a variety of tools have allowed us to do this. But as we prove the concept and then get serious about turning this into chips, we've got to get a bit more market aligned and use what everybody else does and what's expected. So we've gone through the handwritten simulator to industry standard simulation, and then working with partners, so CodaSit, for example. Then the next stage of that, this all flows into a test chip. Now, we're part of Silicon Catalyst. We were on the Chip Start first cohort. We moved into the Silicon Catalyst accelerator incubator scheme, and so this is going to be really, really helpful when it comes to fabbing chips. Get us there quicker. A little bit about performance. You write a lot less code because you're writing, or there are the abstracted instructions. If you're doing that kind of code, it will be supported at a compiler level, but a lot less code to write and debug, and fractional memory accesses, particularly in instruction memory, because that's so small, but also data memory is reduced a lot because of the efficiency, not having to do load stores operations so much. And then actually this number's just jumped up since I wrote this to 5 times. We've tweaked a few things, and we're getting 500% performance increase on 1/5 of the clock cycles to execute a routine compared to standard RISC-V instructions. So it all works. And then over time scale, this is going to get better because we've got a bunch more features to add to the system in the next couple of years, which are going to increase the performance there. Then we're going to integrate into the pipeline. And when you start to integrate into the pipeline, you know a lot better about the processor resources. You can do clever things with the registers. It starts to become like a processor in memory. We can have whatever number of registers we want, and we can parallelize the ALUs or execution units to increase the performance that way. So that just keeps on going. And then, so that was what I just described, the front end moving into the chip itself. We call it VISC IPA, not the beer, but the integrated pipeline acceleration. This, we're going to take it to market as a core, and then as we move forward, we can go into sort of chiplet, enhanced core form. We can then go into customer specific or ASIC type of products, and optionality in the end is to come out with a standard chip. And then what about other processor architectures? Seem to get my acronyms from bad habits, not all mine. So VISC, any pipeline, doesn't work with ARM, it'll work with x86, whatever. It's just whether or not they want us to do it and will pay us enough to do it. So we've got a lot of road ahead of us. And a very quick example, we're working on a project partnership with a blood analysis company that is doing some clever stuff to isolate and allow us to identify, using AI and machine learning, needle in a haystack, you know, a certain type of blood cell that's important in therapy of cancers that only occurs in about 1 in a billion cells. But if you can find it, you know an awful lot about what's happening with the patient. This is funded by a UKRI, Innovate UK grant funding. And the development is going to take us initially through FPGA proof of the AI acceleration with this, and then it'll scale, because it will need to scale to do this in real time, and eventually goes into a product that will be sold by a large company out there. So a few things learned, and a little bit of advice. Don't let the back-end verification stifle your front-end innovation. Solve problems that are real and exist in the marketplace, then worry about that. So make sure you know what the market wants, and once you've done all that, then focus on getting a solution right. Make sure the technology works. The functional verification comes first. And as we did, we designed ways around it post-chip to solve the problems. Then get back to your back-end verification when you want to make a chip and you want to make it in millions and everybody's going to use it, and you need to cover all the corner cases, etc. We've really benefited from partners in this, whether it's CodaSip for the cores, and Innovate UK, and ChipStart, Silicon Catalyst. I think having said at the start that a big chip company failed to impact the other big companies on the market, these days a startup can do it. So that's what we're going to do. So I think if with this sort of mindset, then we can, and everybody can get involved in this or in other aspects of technology development and innovation. I hope that's
great. Thanks very much, James.
Useful.
Thank you. Right. Julie, it's time for lunch, right? Is it lunch?
Time for lunch.
Time for lunch now. So you'll be around for lunch.
Yes, thank you. Yeah.
Oh, right.
Yeah. Yeah.
Sounds like the
Yes, so
we need to.
Yeah.
I can end it. I don't want to end it. You know, put attention.
Beginning of this year. So we're
Is it just like
Yeah,
Simple type run.
in
I was just worried that I might just keep it open, but that's the
yeah,
They're fairly slow.
the webinar, do not just press forward. Okay, so we'll end the event.
About six bits of data.
Thank you.